This time we're going to take a look at 12.2, and in 12.2 you're introduced to exponential functions. And when we look at an exponential function, there's two ways to look at it. We can have something that grows exponentially or something that decays exponentially. So we can start off with just a really simple example. F of x is equal to 2 to the x. To get a feel for this, I can just do a nice little t-table here of x's and 2 to the x's. So if I had an input of, say, 0, 2 to the 0 would be 1. And as I'm graphing this, 1, 2, 3, 4, 5, 6, or whatever, things get really big in a hurry with exponential functions, so I'm not going to get much up here. Okay, if I put 1 in, 2 to the first is 2, so 1 is 2, it's getting higher quickly. 2 squared is 4, so 2 squared is 1, 2, 3, 4 is right here. Oh, I see, I put this one in the wrong spot. Okay, so I'll move that one there, and then 2 is 4, and then 3, 2 cubed is 8, and I'm already off the chart. 1, 2, 3. I went up to 6, 7, 8, so I'll just kind of eyeball it. So you can see, ignore that one, but you can see how it's just increasing very, very quickly. What I didn't put up here for my x's are negatives. So negative 1, 2 to the negative 1. This is a negative exponent, so I'm going to do the reciprocal, and I get 1/2. So at negative 1, it's 1/2. Negative 2, 2 to the negative 2, again negative exponents. 1 over 2 squared is 1/4. So I'm just getting tiny really, really quickly. But I'm going to continue to find values no matter how big I get on the negative side. 2 to the negative 3, I reciprocate that, and I get 1/8. 1/8. But I continue, I never get to 0. So as I fill this in, my exponential function looks like this. So there's my exponential function. Great review from earlier in the quarter. Let's do domain and range. My domain. I can put anything in for x. Everything works. I'll get a really, really big number or a really, really small number, but they all work. So real numbers will work, or you can say negative infinity to infinity. Range. Well, range is a different story. I don't get any negatives out of this. 2 to whatever is never going to be a negative number. I also can never get 0. 2 to a power can never be 0. So my range, I start above 0, so I'm looking at my y values now. So my y values, my lowest, just the boundary is 0, it doesn't include it. So 0, comma, then it goes on up. So 0 to infinity. So there's my range. I have a y-intercept, there it is. So my y-intercept, 0 for x and 1 for y, so it crosses the y-axis at 1. And we say this is an increasing function. It's increasing because I read it left to right just like a book. When I get on the graph on the left side and I move to the right, I'm forced to move up, which would be increasing. So it's an increasing function. So this is my generic exponential. So whenever you're looking at an exponential that has just a positive number for a base that's bigger than 1, you know that it's going to look like this. So this is my increasing exponential. If I were to do another example here right below it and do f of x is equal to 1/2 to the x, or I could write that as 2 to the negative x. Do you see where that negative is? So there's the negative. 2 to the negative 1 is 1/2. So these are one and the same. Well, this one, my base is not a positive number. I mean, it's a positive number, but it's not a positive whole number. It's a fraction. And this one is my decreasing exponential. You can do your own t-table. I'm just going to sketch it. It does have the same y-intercept, but it decreases. So on the left, I start up high, and then I quickly move down. But I have the same properties. So let's see, 1, 2, 3, 4, 5, 6. Is that how far I went? So as I go through my properties, my domain is still all real numbers. Any x will work. My range is still, here's my range, lowest value is 0, so 0 to infinity. And what else do we do? The y-intercept. The y-intercept is 0, 1. The only thing that I changed in terms of its characteristics is the fact that this is decreasing. So I start on the left, like I read a book. I pick up the graph way up here, and as I move to the right, I'm forced to go down. So this is a decreasing exponential. And the difference is that base. So if I have a base that's a fraction, it's decreasing. When I have a base that is a positive whole number, it is increasing. So let's look at some other examples of the graphs of these functions. So here's two really great examples. The nice thing about the exponentials is that they will always, always, always have their shape, and you'll only ever be asked to do a sketch. So if you've got these two in mind, you're going to either graph the exponential going up or the exponential going down. You can come up with a graph really quickly, even more quickly than you could with a fancy graphing calculator. Okay, here comes another example. Let's say that we have, for example, g of x equals 5 to the x. I don't need to do a t-table. I don't need to do anything fancy. All I need to do is to recognize that I have a whole number for a base and a positive x as the exponent. This is an increasing exponential. If I was asked to sketch a graph, it would look exactly the same as the one we just did. Exactly the same. It's a little steeper, but I'm just not going to put a scale there. It also still has the same y-intercept, 0, 1. It has the same domain. It has the same range. If I were to do, like h of x is equal to 1/3 to the x, now I've got a base that's a fraction less than 1, but I know it's going to have that same shape as the second graph that we did, and it's going to look like this. Same y-intercept, 0, 1, same domain. Aren't these nice? Same range. There's so many common characteristics as you move through. But we can move these around a little bit. So we can start to do some transformations with these. And as we're working on transformations, remember anything inside the function is a transformation in the x direction. Anything outside, I don't know why I use parentheses, but I did, anything outside the function operation is something in the y direction. Okay. So let's say that we had f of x equals 5 to the x plus 2. Okay, where's my orange pen? There's the exponential. I know what that graph looks like, which means that this guy right here is the transformation. It happened after the exponential. There's the exponential right there to the x. That plus 2 is on the outside. So it's a change in the y direction. So this shifts the entire graph up 2. I'm going to graph the original function. Let me get myself a grid here. I'm going to graph 5 to the x in orange. Okay, we know what that looks like. There's 5 to the x. Okay, 5 to the x. My favorite point to use as a reference point is my intercept, because it's the same every time. It's easy to work with. 0, 1. I need to take this point and bump it up by 2. The other nice thing to move up is this asymptote. So this part of the graph here that gets really, really close to the x-axis but never touches it is called the asymptotic part. That's a mouthful of the graph. But it's fairly easy to move up. So I'm going to take this shape and I'm going to move it up 1, 2 units. Okay, so 1, 2, 3, 4, 5, 6. Okay, I'm going to start by moving up. I have this x-axis here that was a really nice boundary. But I'm going to move it up with just a dotted line. I need to move that boundary up 2. 1, 2. So I have that boundary up here at 2. Okay, I'm moving everything plus 2. So I moved that up 2. And I need to move up my y-intercept up 2 also. So here was my y-intercept, 5 to the x. Now I'm doing the plus 2 part. 1, 2. Nothing else changes. It's the same shape. I just moved it up. So my graph looks like that. So the graph in purple is 5 to the x plus 2. Let's do another one. So, example, let's say that h of x is equal to, let's do 1/2 to the x minus 1. You see that? So on this one, the transformation is happening with the exponential. There it is. It's not on the outside, it's with the exponential. So that means this minus 1 is a change in the x direction, which all happen in the opposite direction. So instead of me moving everything left 1 because of the subtract 1, I'm going to do to the right by 1. Remember, those are all opposite. We're compensating because it's something we're putting into the function. So when I graph this guy, so if I graph it, where's my paper? So if I graph this one, I'm going to start by graphing 1/2 to the x first. 1/2 to the x. That's my decreasing exponential. I'll give myself a couple of tick marks here. So that's my decreasing exponential. It's not going to be perfect. I'm just going to sketch it. I don't care about being perfect. Okay, so there it is. That's 1/2 to the x. Now I'm going to do that minus 1 part. That minus 1 part shifts everything over by 1. Well, if I shift over the graph, my asymptote is the same thing. I don't move that up or down at all, so I just shift it over. So really, it's just this point right here. That's my intercept. I'm going to move that intercept over by 1 to the right, and it lands right here. I don't care about where it crosses the y-axis, so we're just going to sketch it in. It's not going to be perfect, but we don't care about being perfect, and I go ahead and graph that in. So the graph, but do you see how that just all got shifted over by 1? So there's my graph shifted over by 1. Let's see, so what else can we do with exponentials? So with the exponentials, we are going to move in the next video and start talking about, we'll start talking about inverse functions. So I think out of 12.2, this is probably good for now. And then I'll also give you a video that will talk about what you need to focus on for that upcoming exam. So I'll give you an idea of what to be studying.